In the previous class, we learned about the several hybrid mapping mechanism in SSD. So actually, we learned that why the address translation is required in SSD. So that means this address translation is required. SSD has very asymmetric characteristics for read and write operations. So if this characteristics is not does not have a very wide gap so between read and write operations, then we can apply the very simple translation, or we can apply the very simple NAND flash management schemes in SSD. But problem is that the SSD is the non-volatile memory, and then the characteristics of this non-volatile memory is very different from the volatile memory such as SRAM or DRAM. So actually, there are many kinds of non-volatile memories, and then the academia or industries are developing new type of non-volatile memories such as PMEM or STT-RAM or memristors. But usually, usually the write property of these non-volatile memories is worse than the property of read operations. So usually the read operation is very fast, but the write operation is very, very slow. So, but because this write operation is very, very slow, then we need to apply some research ideas to these non-volatile memories. So that's also true for the other non-volatile memories such as STT-RAM or PRAM, okay, or memristors. So we need to avoid this number of writes to the non-volatile memories. So that means that we need to reduce the number of writes to the non-volatile memories. Okay, and then these policies also can be applied to the SSD because the SSD use the flash memory as their main storage media. Also, we know that the performance of the write of SSD is 10 times slower than the read operation. So, okay, so that means we need to reduce the number of writes to the SSD. Also, another property of the flash memory is that the granularity for read-write operations and erase operations are different. So we already know that. So access granularity for read and write is page, and then also the access granularity for erase operation is block. So block is composed of multiple pages. We learned that why the erase requires a very large granularity compared to the read and write operations. Okay, because the erase operation to then the flash memory requires very high energy. So because this very high energy is associated to the NAND flash memory cells, the data stored inside of this NAND flash memory cell can be corrupted by very high energy. So that's why we apply the block granularity for erase operation. Okay, so that's why we need the address translation in SSD. And then, but what's the problem of this address translation mechanism? So actually, this address translation is also applied to the virtual memory. Okay, so what is the what is the problem of this virtual memory? So the problem is that it's low performance. Okay, so in order to manage in order to apply the virtual memory schemes, operating system need to manage the translation table inside of DRAM, that means the main memory. Okay. If we apply this address translation scheme very so directly, that means the page level translation, then the size of this virtual memory translation table may be very large. So in order to reduce the size of the virtual memory address translation table for virtual memory, then we apply the multi-level address translation. So, and then what is the issue problems in this multi-step virtual address translation in virtual memory? So that means that disadvantage is also performance. Okay, because in order to access the multi-steps, the multi-level address translation table, then we need to access DRAM multiple times. Okay, and then that will degrade the performance of the virtual memory. But the NAND flash memory, the property of NAND flash memory is different from that of DRAM. Also, for this NAND flash memory, then we need to the first goal of this address translation in SSD is to reduce number of write and number of erasure. Okay, these are the goal of efficient address translation in SSD, because the write performance to NAND flash memory is very low. Also, the erase requires very large number of cycles in the SSD. Also, the NAND flash has limited number of writes. That means that the limited number of erase. So we need to reduce this erase count in NAND flash memory. Okay. So what is the best? So what is the best address translation scheme for SSD if we just consider the performance of SSD? That is page level mapping. Okay. So with the page level mapping, then we don't need to consider about this number of writes or number of erase, because the read-in operation is performs at page granularity, and then if we just find an empty page inside of NAND flash memory, then we can perform write immediately. And then if the invalid blocks are many invalid blocks are generated inside of a block, then we can perform erase. That is called the garbage collection. But the disadvantage of this page level mapping is the large translation table. Okay, and then actually this translation table is managed in the DRAM of SSD. That's why the SSD has DRAM. Also, DRAM can be also used for data buffer between this SSD and host CPU, but also SSD manages this address translation table inside of DRAM. So if the size of this address translation table is very large, then the SSD requires the very large DRAM. Okay, then there is also that will increase the cost of SSD. So that's why the SSD has the lots of research topics. Okay. Yeah. So in the previous class we learned about log block scheme, the past. So we learned about the pros and cons of page mapping or block mapping mechanisms. So I said the one solution will have pros and cons. So if a solution have only advantages, then it's not real solution. It's not a real solution. Okay. So so we can know that the advantage of a page mapping is the performance and efficient management of the net flash memory. But the problem is that it's a large translation table, and then also the advantages and disadvantages of block mapping is that so we can reduce this translation table with the block mapping mechanism, but with this block mapping mechanism, the write operation, the write to the SSD requires the more writes to the net flash memory. Okay, so we learned it, and then this is called the write application. So that means that the operating system, that means the host system just gives the one write operation, but this write operation causes the more write operations to NAND flash memory. That is called the write amplification. Okay. So inefficient management is the disadvantage of this block mapping mechanism. And then in order to handle the disadvantage of the block mapping mechanism, some hybrid mapping mechanisms are presented. And then so in the previous class we learned about the log block scheme. So this log block scheme is actually some old research paper, and then this log block scheme is called the best. Okay. Actually, this log block scheme is very similar to the log structured file system in the storage devices. So actually, operating system, the file system, or the operating system research area, the operating system knows that the write operation is also very low performance in storage devices, and then so that means that the file system also avoids the write operations. So that means that the file system needs to reduce number of writes to storage devices. And then for this reason, the file system developed the log structured file system. So the log structured file system means that so when the write is performed by operating systems, then we just write the updates. That is called the log, and then this log is returned to the storage devices. And then after that, this log is updated to the real file, in the real file data, and that is called the log-based file system. And then the very similar ideas can be applied to the SSD. So it is because the write performance is very low, and then we need to reduce the number of writes or number of erase inside of the SSD. So I explained that in this log-based scheme, the log block is associated with the data block, and then if the new write is given to the SSD, then this new write page operation is performed in the log block. Okay, and then Also, this is the hybrid mapping mechanism. So for the normal data block, the block-based mapping mechanism is applied. And then for the log block, the page level mapping mechanism is applied. But the number of log block is limited inside of the SSD. So that means that the SSD just assigned the small fractions of log blocks. So this is the some flash memory, and then SSD are assigned the so for small fractions for log blocks. So if all log blocks are consumed by this associated data block, then you need to perform merge operation. So that means that the log block is with this log blocks, the data inside of the log blocks, and then existing data blocks, then we generate so we create the new data blocks. That is called the merge operation. And then actually this merge operation is the performance overhead of hybrid mapping mechanism. Okay, because the merge operation creates additional write to request to the NAND flash memory. Also, this merge operation creates erase operation to NAND flash memory. So with this merging, it performs more writes and erase. That is the performance bottleneck of this hybrid mapping mechanism. So we learned the additional required operations for this different merge operations by the BAST. So we can compute some performance overhead by this BAST scheme. Okay, so that's the problem. So in order to handle this performance overhead of BAST, then the new scheme is also developed, and then this scheme is called the FAST. So this is some idea. So this is the paper for representing FAST. So it's a log buffer-based flash translation layer using fully associative sector translation. That's why this scheme is called the FAST. Okay. So, and then this previous idea is called the BAST because usually this log scheme is called the block associative sector translation. So it's a BAST. Okay. So usually our research starts from some issues of the previous research work. Okay. So what's the issues? What are the issues in BAST? That's the log scheme. So the issues of BAST are the first, this log block is associated to data block. Only one log block is associated to data block. And then inside of the log block, this BAST applies the page level mapping mechanism. So what is the page level mechanism? If the logical page number is given to this page translation table, then this page translation table makes the physical page address. Okay, so that means inside of the log block, this logical page number is only the limited number of logical page numbers are assigned. So for example, if this data block and the log block has only 4 pages, then we can assign only 1 to 0, 1, 2, 3 logical page numbers for this log block. Now, what's the problem? Only a certain block. So for example, this logical page number 1 can be updated frequently. So that means 1 is written, the logical page number 1 is written, and then 1 is written, 1 is written, 1 is written. So for this case, this best scheme cannot handle this case. So that means that if a certain page is frequently updated, then for this case, we apply the log block again. We assign this log block again and again to the corresponding data block. So the space of log block is wasted. So that's the problem. So the first issue in BAST is the low space utilization of log blocks. Okay. So that means that the entire pages in log blocks are not utilized, but this log block is replaced to the new log block. So the authors of this first paper presented that this log block scheme is the block associated sector translation approach. It's called the BEST. So usually we call this log block scheme as BEST. Okay, because this log block has the log block is only one log block is associated to data block, and then the SSD was some flash-based storage devices just manage this log block based on the block-based association. Okay? So that's the problem. So the problem is the low utilization of log block. So I already explained about these issues. Also, the log block tracing is done another. So that is also related to the low utilization of the log block. So this is called the log block tracing. So it's very similar to the cache tracing. Okay. So that means that only some part of the pages inside of a log block is used. So that's what I explained. Also, the intensive override, it's also similar issues of this log scheme, the BEST, the block associated sector translation. So because of this property, then the pages inside of a log block is wasted. So that means that the log block has many empty pages, but the log block should be replaced. So that's the problem. So how can you avoid this case, this situation? So actually, every idea is not new. So actually, we learned from the old ideas. So the first, let's think about the set associative cache or direct mapped cache. What's the problem of this set associative and direct mapped cache? So the problem of set associate or direct map to cache is that even though cache has empty blocks or certain access to this cache cannot use these empty blocks. It is because some addresses, that means that some request to this cache is only assigned to the or certain set or also certain blocks inside of this set associated cache or direct mapped cache. But what is the benefit of this set associative cache? Then we can reduce the hardware resources for this kind of caches. Okay, so the space is wasted, but we can reduce the hardware cost. And then in order to reduce this wasted cache blocks, we can apply fully associative cache. So with the fully associative cache, the accesses to this fully associative cache can be assigned to any location of cache. So with this fully associative cache, we can reduce the wasted cache blocks. Okay. So well, what is the benefit of, so we already know that. So usually we know that the performance of the set associated cache is similar to that of a fully associative cache. If we increase the associativities of the set associative cache. So usually we use the 4-way or 8-way cache, and then we already know that the performance of this 4-way or 8-way set associative cache is enough. But why is this true? So we know that with the we know that the fully associative cache will have highest performance because we can reduce the conflict misses. But we know that with the 4-way associative cache or 8-way set associative cache, now we can get the similar performance. Why? Why? Because the accesses to cache are usually random. Do you understand what I said? It depends on the access patterns. Okay, the performance of the cache depends on the access patterns applied to the cache. Because the access to this set associated cache is usually random, then we can apply the multi-way set associative cache, and the performance is nearly similar to the fully associative cache. So what can you run? The performance of, so usually memory or storage depends on the access patterns. Okay. So we know that page level mapping. This page level mapping is very similar to this fully associative cache actually. Because pages are one-to-one mapped to the so logical pages are one-to-one mapped to the physical pages. So this page mapping is very similar to the fully associative cache, but we don't need to apply the page level mapping to all kinds of accesses to storage. because the accesses to storage is composed of first sequential accesses or and random accesses. So we know that actually every access to the storage devices are composed of these two types of requests, the sequential accesses or random accesses. So we can, so what's the issue of this best? So with the best, we can apply the log blocks, but log blocks are only one log block is associated to data block. So that also limit the some mapping mechanism, so mapping policy. So that means the address translation policy, which is similar to the set associative cache. Because the accesses to storage are composed of random accesses and then sequential accesses, and we can apply some more flexible address translation policy. And then this more flexible address translation policy is called the fast. Okay. It's similar to this fully associative cache, but only the part of block applies the fully associative cache-like address translation or address mapping mechanisms. Okay. So this paper starts from some observations, and then this observation is that the space utilization of log block. Okay, that is the start of our research. So our research starts from some observations, and with these observations, we can know the issues or problems of existing solutions. Okay. So what are the issues? As I explained, the low utilization in log blocks. So there are three patterns. So that means some access patterns to the storage devices. So as you can see, the utilization of the log block is very low. So the x-axis represents the number of log blocks, and the y-axis shows the utilization inside of this log block, as you can see. So there are various patterns. So pattern A, for the pattern A, this utilization is very low. For the another patterns, the other patterns, the utilization may be high if the number of log blocks are large. Number of log block is large, but for some patterns, I think it's some random writes. This pattern may have very large portion of random writes. So for this random access patterns, then the utilization of the best, then the utilization of the log block may be very low. That's the problem. So the authors of this paper just observed that the problem of this best is some granularity of the block association. So problem is that only one log block can be assigned to one data block. And then I also explained what's the problem, some scenarios that cause the low utilization of this log block. So if there are repeated writes to the certain pages, then we need to replace the log blocks. Okay. So in order to avoid this case, so like this cache ideas, we can apply the fully associative mapping to log blocks. Okay, and that's why this is called the fast. So with this idea, the one data block can be associated to multiple log blocks. So then also the another data block can be also associated to the different log blocks. So with this mapping, then we can increase the utilizations inside of a log block. And what's the problem? What's the problem of this scheme? So first, what is the problem of fully associative cache? Hardware cost. Okay, also the design is also complex. Also, the problem of this fast is the also complex mapping algorithms. And then also this log block is multiple log blocks can be applied to the multiple data blocks. If the log blocks, all log blocks are wasted, then also we need to perform the merge operation. And then for this merge operation, the performance of this fast can be also degraded. Okay, because so actually this mapping is very similar to the page level mapping mechanism, right? So actually the idea of the best is that for this log block we can apply the page level mapping, but this page level mapping is restricted to inside of a certain log block. With the fast, the authors remove these limitations. Okay, so that means that the page level mapping can be applied to multiple log blocks. Okay, that is the idea of the fast. So that means that the first, in order to perform the merge operation, this SSD controller need to find the appropriate pages in the multiple log blocks. Okay, and then they will also requires the very complex operations inside of SSD. So there's a complex management or complex mechanisms of this random place management in SSD is the problem of fast mapping. How can you also solve? How can you solve this problem? So that means with the fast, then we need to perform only full merging, not this partial merging or switch merging, without this fast mechanism. Right? Because some recent pages can be found in different log blocks. And then for this merge operation, we need to perform the full merging. Okay? We need to find some appropriate pages inside of multiple blocks, and then we can regenerate the data block, and then this newly generated data block can be updated to the block mapping table. So actually the overhead of the merge operation of the fast is just it's similar to the full merge. How can we solve this issue? If we apply the switch merge operation, we can reduce the overhead for this full merge, but with this fast mechanism, then we can only apply the full merge like merge operation. So that's the problem. We not to avoid reduce this performance overhead by full merge, then fast also supports the two kinds of log blocks. Sequential, the log block that supports the sequential write, and then a log block supports the random write. So this with this sequential write log block, we can apply the switch merging. We can just, so that means the pages are written sequentially, then we can just replace this block to the another data block. Okay. So why do we need these complex mechanisms? Because as I explained, the access patterns to the storage are composed of sequential write and then random write, and that's the problem. So, and then the storage devices are developed for supporting both access patterns, so like sequential write and then random write, and then the storage device also need to support the high performance for both kinds of write operation. So with the fast is good for the only random write, but without this random without this fast mechanism, we need to perform the full merge, and then full merge also cause higher performance overhead. And then in order to avoid this situation, also the fast has also some specialized log block called the sequential write log block. Okay, so that means that if a certain write is determined as the sequential write, and then this write is done inside of this sequential write log block. Okay. So there are three kinds of blocks inside of this fast architecture. So that's the normal data blocks, it's the same to the fast, and then page level mapping table for the sequential write. So this is the sequential write log block, and then page level mapping for random write. So random write log blocks. Okay. And first, what is the problem of this mechanism? So there are three kinds of the block. So it's the sequential write log blocks, and then random write log blocks. What's the problem? What is the another issues? What is the another issue to be solved? So another issue. What is the another issue? We need to decide. The property of write. The storage device is the passive device. So storage device does not know what is the sequential write, and then what's the does not know what sequential write is. The current write is the sequential write or the random write. So actually the operating system knows, but storage device does not know, because storage device just receives the very simple commands such as read, write, erase to a certain sectors. So storage device does not know the current write is sequential write or random write. But in order to use this sequential write log block, the storage device decide, the current write is sequential write, or the current write is random write. Okay, that's the another issue of this fast. And how can we decide the kind of the property of write to the storage device? So the authors of this paper just categorized some kind of write to the storage device, like so these cases. So number 1, 2.1, or the resolution is not good, but so in this slide, 2.1, 2.2, 3. Okay, so let's see these cases. So that is just a rule that is used by this fast mechanism. Okay, it's not a exactly correct rule. So that means that this rule can be incorrect. So this observation can be incorrect, but that is just the estimation. This is very similar to the prediction approach inside that is used in the CPUs. Okay, so because the storage device does not know the property of a write given by operating host system, then just the storage system just estimate the kinds of write, okay, based on the some write sequences or some write request inside of the request queue in SSD. Okay, so let's see some sequential write cases or random write cases. So what is the case 1? Case 1 means that the logical page number of this write request is the first page of block. Okay. So in this case, the best architecture just consider this request is the start of sequential write. Okay, because that is this logical page number is the first page of a certain block. So that can be inefficient because the random write can be also a part of random write can be also request the target the first page of the log block. But this is just a rule. So the best consider that if the logical page number of the write request is the first page of the log block, then best consider this is the start of the sequential write. So this write request is written to the sequential log block. And how about this 2.1 case? This is also the sequential, the next page is requested, the next page is requested for the write, and then so this is the kind of part of the sequential write, and then the sequential write starts from the first page of the block, flash block. So in this case, the FS also consider that this write request is the sequential write. Okay. How about this case? So actually, for this request, the start is the first page of the block, but the next request is the 6. So this is actually, this is not a sequential write. So in this case, so we only know that if this request for this logical page number 4 is given to the SSD, then this page is assigned to the sequential write log block. But for the next request, the next write request is allocated to the some is now allocated to the neighbor page. So it's allocated to the some next pages. So in this case, the sequential write is broken. So then in this case, the SSD just merge this sequential write log block to the data block. Okay. So that means that this sequential write block can be this log block cannot be used for sequential write. So that means the fast SSD just performs the merge operation with the data block. So like case 3. So the case 3 means that this write, the first write to this SD just to write the second some other pages inside of the log block. So this request cannot be assigned to the first page in this log block. So in this case, this write request is assigned to the random write log block. Okay, that is the write operation. And then with this sequential write log block, the fast also can perform the switch merge or partial merge, because the write operation to this log block is performed sequentially. So we can use the two kinds of the simple merge operation and switch merge and the partial merge, and that's also simple. So the all pages of this sequential log block is written sequentially, then can just switch the block mapping information to this switch sequential write log block. It's called the switch merge, and then this is very simple. And then with the partial merge, then so pages are partially updated, but these pages are sequentially updated. And then there are some empty pages in this sequential write log block. For this case, we can perform the partial merge, where we can just read some pages from the data block, then we perform this partial merge. So with this switch merge, the SSD does not have any performance overhead. The SSD, because the SSD just switch the block mapping information. But with the partial merge, then the SSD needs to perform the write operation for these partially updated pages inside of the data block, and then just change the block mapping information. So this partial merge just requires some write. Okay. So with this sequential write log block, then we need to perform the full merge. Okay, that's the problem. So that's why the fast has the sequential write log block. So let's see the scenario of this case. So for this scenario, this is the write sequence to the SSD, and then we assume that the fast has the only random write log blocks. So we can apply the page level mapping for this random write log blocks, and so we assume that this logical page number is assigned to the pages of this random write log block. So as you can see, there are two log blocks, then two random write log blocks. So as you can see, the logical page number 7 is assigned to this page A, and then page number 0 is assigned to this page B. we know that this logical page number 7 is here, and then logical page number 0 is here. So these logical page numbers are this logical page number exists across multiple data blocks, but these pages can be assigned to the same random write log blocks. Okay, that is the some unique feature of the fast. Okay, so without this sequential write log block, then I said that we need the only full merge. So in order to perform the full merge, then we need to find some pages that is associated to a certain data block. So for this case, we in order to make a certain log block empty, then we need to find the appropriated pages associated to a certain entire data block. Okay. So in this case, in this example, this page number 0, 1, 2, 3, and 5, 7, and 11, 15 are newly updated. So actually, the pages for this logical page number exist in random write log blocks. And then if there is no available space inside of log blocks, then we need to perform the merge operation. So in this example, this data block has all updated pages. Okay, then with this information, we can know that we can make the new data block from the log blocks. So in this case, we can find the available pages inside of log blocks. So 1012 is assigned to the pages of B, C, D, and then F of the another log block. Okay, then we read these pages and then performs the write operation to the empty blocks, and then we just switch this block to this data block. Okay, that is the full merge. Okay, and then how about this 4, 5, 6, 7? So actually, in this example, then we can find the logical page number 5 and then logical page number 7 in the log blocks, and then but we cannot find 5 and 7 here, but we cannot find these pages inside our log block. Okay, so in this case, we can read the E and A from log block, and then we can read the 4 and 6 from the data block, and then we can make the new blocks, and then we can replace this block to this data block. Okay, this is also full merge. And then not to make the new empty log block, we need to perform the erase operation. Okay, so in this case, this the old pages inside of this log block is updated to the new data block. So we can erase this log block. Okay, so we can perform the erase operation for this log block. Also, we can perform the erase operation for this data block. So this operation will cause 2 erase operations. Okay. So then let us assume that we can, so with this merge operation, the one empty log block is generated. And then new write operation is also given to this SSD, like logical with the logical page number 0. Okay, so in this case, then this request is assigned to the random write log block, and then this page is pointed by logical page number 0. Okay. So with this so this is the first page of the data block, but this page is assigned to the random write log block. So that means that even though the future request is performed sequentially, then we need to also perform the full merge for this case. So not to avoid this case, the fast has the sequential write to log blocks, then this sequential write is stored in the sequential write to log blocks. And then we can perform the very simple switch merge or partial merge with the sequential write log blocks. Okay, like switch merge. Okay. So actually, the merge operation is the very critical for fast architecture. So with this random write log blocks, we need to find the victim. Then that means that we need to find some pages that is used for generate new data block. Okay. So that means that these pages can be found in the different log block. Okay. There's also some critical issue of this fast mechanism. So this slide just explain how to select the victims from the log block and then generate the new data block. Okay. So the victim is selected, then this corresponding page is invalidated, and then the data inside of this page is copied to the new block. And then if this new block is generated, then you can erase a certain log block, and then you can map this generated block to the new data block. Okay. So this is the merge operation, and then you can erase some. So with this past mechanism, then we can reduce some number of erase, or we can also increase the performance. Okay. So this slide shows the performance of the fast, and then the authors compare the performance of a fast with the previous work called best. Okay. This graph shows the number of erase count, and then this graph shows some elapsed time. So there's a total elapsed time to the storage devices. Okay. So then, so also just compares the fast, and then all fast. Or I don't know what this all fast. Then, as you can see, this erase count, we can know that the erase count is reduced. Okay, and then as the erase count is reduced, the elapsed time to the storage device is also reduced. So that means that the performance of the storage device is improved with the fast mechanism. Okay. So there are different access patterns, and then these streams are captured from the different applications such as digital camera, and then so Linux, and then it's a several random write. So can you observe? So you can know that actually for this random write patterns, then performance of fast is it's much better than the performance of fast. So as you can see, the erasure count is dramatically reduced, and then also the performance is improved. For it's right, random write. Okay, but this is the performance improvement for random writes. So, and then as I explained, we know that the requests to the storage are composed of random writes and then sequential writes. So this is a very some what's that? It's a two so two ideal two ideal case. Okay. But we can know that fast mechanism is good for the random writes. Okay. So these are the advantage and disadvantage of the fast. And then also we can know some advantage or disadvantage of the fast mechanism. So what I want to say is that actually some real workload is composed of various kinds of access patterns like random write or sequential write, and then our solution need to support these both cases, and in order to support these different access patterns or different kinds of applications, when we need to divide some unique features of these workloads like sequential write and then random write. So we need to distinguish the different kinds of access patterns. And then after that, we can apply some specified ideas for different kinds of workload like sequential write or random write for some another approaches for the random write. So why this is necessary? Why is it necessary? Because so actually we are working on the computer system. So and then the computer system is developed for general purpose application, and then these general purpose applications have the mix of different characteristics of workload. So in order to support these different access patterns or different type of workload, then we need to first analyze some characteristics of the target workload. Then we apply our ideas for some different kinds of workload. Okay, that is some research approach or some research how we can develop our ideas for some research. Okay, so let's take a break for 10 minutes. So do you have any questions for this fast mapping, fast architecture? Okay, let's take a break, and then I will be back at 11:55. Okay, let's resume the class. So actually, this address translation in SSD is very interesting. So it's a very interesting. There are many interesting approaches in the SSD. And then, so actually, I think only one solution cannot solve every aspect of this write access patterns. Also, the flash memory has it's more complex than the DRAM operation. So the flash memory has the very unique characteristics in read, write, and erase operations. And then these operations are very asymmetric. So again, I think the SSD or flash memory has lots of interesting research research issues or research topics. Actually, but this address translation is very interesting. We can apply the some specific address translation scheme to solve a specific issues or specific behavior of the access patterns to storage devices. But the problem is that a specific address translation approach cannot cover entire respect of the write request to storage devices. Also, we need to consider some additional issues such as the number of erases or where labeling inside of this SSD. So the problem is that and the flash memory has limited number of writes, that means that limited number of erases. So we need to apply the garbage collection to block erase carefully. So if the erase count is very high, then the lifetime of the SSD may be reduced. And then there is also some critical cost issue of the SSD. So this is another interesting research topic of SSD. So if you search for some research papers in the SSD research area, then you can find that there are many papers that handles the lifetime issues or reliability issues in SSD. Okay, it's very interesting. Okay, so let's talk about another address translation ideas in SSD. So then this idea is these ideas are different from the hybrid mapping mechanisms we learned in the previous and today's class, because these ideas apply the page mapping mechanism. Okay. These are the flash memory summary. Okay. So we also learned about the benefits or disadvantages of page mapping and block mapping mechanisms here. So now I will introduce the demand-based FTL called Dftl. So the title of this paper is the Dftl. It's a flash translation layer employing demand-based selective caching of page level address mapping. So we can find the two unique features like some mechanisms used by authors of this paper. So it's a selective caching and then page level address mapping. So this paper just applies the page level mapping mechanism, and then that means this page level mapping mechanism is good for random write or random accesses to SSD. Okay. Page level address mapping. So, but we already know that with the page level mapping, the size of the address translation table matters. So the authors applies the caching mechanism. Okay. So the author applies the very traditional techniques called caching. Okay. we can apply the same approach to our research area. Okay, so why do we need cache? Because the memory is very expensive, such as SRAM memory, or DRAM is also expensive. So we know that SRAMs or DRAMs are very fast, but because of the high cost of this memory, then we apply cache mechanism. Okay. So but why can we use this memory hierarchy like caching mechanism? Because of locality observed in applications. So the main idea of demand-based Dftl, so as you can see, this is the demand-based. So that means we can classify high demand request or low demand request to the storage devices. And then this demand-based approach is similar to the locality-based approach is the caching. So that means that the highly demanded pages, so we can store this page mapping information inside of cache. So what is the cache? Cache in SSD. So cache is the fast memory and but expensive and small. So what is this kind of memory inside of SSD? Which right. So actually, the authors of this paper used the SRAM because this is also somewhat old paper, but DRAM is fast memory and expensive memory and small memory inside of an SSD. But then what's the large memory? It's a very slow, cheap, and then high density memory in SSD. It's flashy memory, right? So main idea of this paper is that, we can use the page level mapping, but what is the disadvantage? What is the disadvantage of page mapping? The disadvantage is that the large address mapping table. But we know that the all information inside of this address translation table is not used. And then if the request to storage device has locality, that's the locality, then we can apply the caching mechanism to manage this large translation table. So main idea is that the frequently used address mapping entries, the frequently used address mapping information is managed inside of DRAM or SRAM in SSD, and then the other entries of this page mapping table is stored in the flash memory. That is the main idea of demand-based Dftl. It's simple. So like this caching mechanism, we can manage this location of the address translation information. Okay, like this cache, like cache. So some frequently used frequently used pages are managed inside of the DRAM, and then other page mapping information is stored in the flash memory. That's the main idea. But we need to consider some complex characteristics of flash memory also, because this mechanism will create some more issues like garbage collection or where leveling issues inside of the SSD. Okay. So let's see. This paper. Okay. So we already know that the page level mapping is good for random writes. Okay. So in order to support this page random write, we learned about the hybrid mapping called the fast and fast. But we already know that this mechanism is not easy. It requires the complex management algorithms, and then also this fast and fast requires some additional arrays or additional writes for merge operation. Then in order to avoid these merge operations for random writes, then if we apply the page level mapping, then we can avoid this high performance overhead by merge operations. That is the main idea of this paper. And then, so this the paper starts from the basic picture of the flash memory. So we already know about this basic picture of the basic characteristics of the flash memory, because I mentioned repeatedly. But so think like this. So usually the mapping information is managed inside of the SRAM or DRAM. That is the actually volatile memory. So what's the problem? If the power is off to the computer systems, then the power to this storage media like SSD is also turned off. Then how can we manage this mapping information? So why do we need the persistent memory? Even though the power failures or power loss of the computer systems, we need to store our data inside of the persistent memory. So in order to avoid the data loss by power failures. That is the purpose of persistent memory. So we use the SSD as the persistent memory inside of the computer systems, but SSD has also volatile memory, it's a DRAM or SRAM, and then this mapping information also should be maintained inside of the SSD. So how can we store this mapping information even if the power is lost or power is failed in the entire computer systems? So SSD has the non-volatile memory actually. Non-volatile memories like flash memory. So this mapping information is stored in the flash memory. So when I explained about the feature of the flash memory, then I also explained about some additional ECC area inside of flash pages. Okay, inside of a flash page. So flash page is composed of data area and ECC area. Actually, I call this area is the ECC area, and that this ECC area stores the additional parity bits for error corrections. Okay, and then data is stored in this data area of a flash page. And then actually this ECC area is called the of band area, and called the OOB. And then this OOB includes the additional data such as the logical page number and then state of the this corresponding page, the current page. So a flash memory page has the page like this. So data is stored in this data area, and then this OB area. OB area has the parity bit for ECC and additional information such as the logical page number, LPN, and the state of this page, like erased. Erased means that it's empty. The valid means that the data is written to this page, and then invalid, the data is invalidated. So this state is also written to the out of band area of the flash memory. So even though the power is lost in the SSD, this information is already stored in the non-volatile memory, the flash memory, and then during the start phase, the restart operation, this information is regenerated from the out of band memory. Okay, so the SSD reads this additional information. Actually, this logical page number and the state of the page is read from the each flash memory pages, and then SSD regenerate the mapping information. Okay? That's how the SSD stores this mapping information, even though the power is off or power is lost in the computer systems. Because this is the non-volatile memory. So also this is what I explained in the previous classes, like page mapping, some flash translation layer functions, also performs the flash management functions like address translation, garbage collection, and where labeling. Okay, so we learned about the page level FTL, page level mechanism, and then prolong level mechanism. I repeatedly explain about the advantages or disadvantages of these two kinds of mapping mechanisms. So we learned about the hybrid FTL. Okay. Then what is the problem? For this hybrid FTL, the SSD needs the additional storage space for log blocks. So we already know that the SSD has the additional spaces, like some additional storage spaces in the flash memory. So I said that the actual storage space of the SSD is larger than some official so shown storage. So that's the specification of the SSD. And then these additional spaces are used for some other purpose, such as some additional spaces for write operation or log blocks, and then some additional for the another purpose. Okay, but usually due to the cost issue, the SSD cannot assign large log blocks in the flash memory. So usually this log block is the 3% of the total flash size. So if the log block is full, then it's filled with the log block is full, then we need to perform the merge operation. And then the merge operation is required. Then as we learned, these merge operations require many erase operations or many write operations. So that is the problem of hybrid FTL. So then this operation is called the garbage collection. So garbage collection can be applied if a certain data block has many invalid blocks, but for the hybrid FTL, this garbage collection is applied when the merge operation is required. Okay. So that is the issue. Those are issues in hybrid FTL. So we learned about the switch merge, partial merge, and full merge. And we learned that the performance overhead by full merge is very heavy, so very high. So you need to avoid this case, the hybrid FTL. But also with this hybrid FTL, this management scheme is very complex, and then also the hybrid FTL requires the additional erase or write operations to merge operations. So that is those are the issues in hybrid FTL. And in order to tackle these issues, we can apply to some very fancy ideas that use the hybrid mapping mechanism, but you already know that the page level mapping mechanism is better for random writes, and then hybrid FTL is actually designed for handle random writes. Okay, so if the page level mapping is better, then we can apply the page level mapping. The problem is that large translation table size, and then we can tackle this issue with the caching mechanism. That is the main idea of this Dftl paper. Okay. So this is the architecture of Dftl, and then as you can, as I explained, this mapping table is stored in the, so this paper used the SRAM, but we can use the DRAM, the SSD, use the more SSD. So it's a DRAM, SRAM or DRAM. But this table mapping table, it's address mapping table is the cached mapping table. So that means that the entire mapping information is not stored, cannot be stored in the DRAM because DRAM size is small. So actually, so this Dftl stores the part of mapping information in the cached mapping table. Okay, and then other mapping information is here. Then other mapping information is stored in flash memory. So this mapping information is stored in the translation blocks. Okay, so this translation blocks has the entire mapping information, the flash memory. Then we need to know the location of the translation blocks also, because these translation blocks are also stored in the flash memory. Then what is the problem with the flash memory? If a certain data is updated, certain page is updated, then we cannot perform the in-place write. So we erase the entire block and then we write the updated content to the new empty blocks. That is the property of the flash memory. And then as this translation block is also stored in flash memory, and then the same mechanism should be applied because it's a flash. So this translation block is also pointed by global translation directory. So this global translation directory stores the physical location of these translation blocks. Okay, so this is some large data. Then this is the cached data mapping information. And then also the data blocks are stored in flash memory. Okay? That is the Dftl architecture. This is very similar to the architecture of the virtual memory, right? And cache. Actually, the virtual memory uses the caching mechanism. So some part of a page is stored in the storage, and then some part of a page is stored in the DRAM. So main idea of the virtual memory is to use DRAM space as cache, like cache. So the DFT architecture is also similar to this virtual memory ideas because the size of the translation table is very large, and then so the SRAM or DRAM, the SSD manage the cached mapping information in the SRAM, DRAM, and then the other mapping information is stored in the flash memory. Okay. So an interesting idea. So then when the virtual memory is applied, then we can think the how the pages are requested and then how pages are accessed in the virtual memory. It's like so the page is found in DRAM, where a page is found in storage. That is the page fault actually. That is the scenario of the virtual memory. That can be also applied to this Dftl architecture. So with the Dftl, if the page is requested from the host, then this page mapping information can be found in the cached mapping table, or it's a hit case, or the mapping table can be found in the flash memory. It's the miss case. So we need to support these two cases, like with the Dftl. So the first case is that the LPN is requested from the host, and this LPN logical page number is found in cached mapping table. That is the best case. This is the actually hit case. So in this case, this mapping information is serviced from the cached mapping table, and then that's it. Okay, it's very simple. With this case, so in this requested information is not found in the cached mapping table, this is the miss case. And then we can also classify this miss case as when the CMT is not full, so CMT has the empty entries, or the CMT is full. So if the CMT is not full, then we can, the miss happens in the cache. And then if the cache is not full, then we can just allocate the new data to cache. The same. Okay. So this is the case 2. The request misses in cached mapping table. So that means that this mapping information is not found in this cached table. Then we can know the location of the entire mapping information, the translation blocks, and then we can know the location of the target translation block by accessing global translation directory. So we just access the global translation directory, and then we figure out the physical location of the translation block, and then we can find the mapping information from these translation blocks. And then this information is updated to the cache. cached mapping table. That's it. There is a miss case, but the cache is not full. Okay. Okay. The another case is that it's missed in cached mapping table, and then this table is already full. So in this case, we need to perform replacement. Okay, the replacement for this cached mapping table. So when the cache replacement is required in the normal cache memory, then we need to apply cache replacement policy. So first, we need to select a victim. So that means that a certain entry should be evicted from the cache. Okay, we need to select a victim. And then another problem is that if the victim is dirty, and this information should be updated to lower level memory. That is how cache works. So it's the same to this cached mapping table. This in the cached mapping table, and then this table is full. That means first we need to select a victim, and then if the victim is dirty, then this information should be updated to translation blocks. So on the flash memory. Okay. Okay. So the Dftl architecture, we can select a victim with a very LRU-like approach. And then if the victim is dirty, then translation block is updated. But actually, this case is the worst case of the Dftl. So let's see how this worst case is handled by Dftl. So in this example, this is the cached mapping table, and then from the host, first want to access the logical page number 1280. But as you can see, this is not found in this cached mapping table. So first, the host access the SSD access the cached mapping table, but this requested page is not found in the cached mapping table. Then also the CMT is full. The first minute is a miss case. So first we need to select a victim. So this is the selected, and then this victim is dirty. So the victim should be evicted from the cached mapping table and dirty. Then this information should be updated to flash memory. So in order to update this information, we need to find the stored translation table inside of the translation blocks. And then this information can be get from the global translation directory. So in this example, the LPN number is the 1. Then let us assume that each translation block has the 512 translation information. Okay, like here. So because the DLPN is 1, then we can just access this number 0. That is the so in this paper, the authors call this is the virtual page number. Why I don't know why it is a virtual page number, but it's some block number of this translation block. And then as you can see, because the LPN is 1, then we can easily know that the block number for this translation block, this is the logical block number, is the also 0. Okay, because 0 will include the logical page number 0 to 5011. Okay, so with this global translation directory, we can get the physical page number for the address translation block. So we can access the here. But this information should be updated to this target translation block. Then in place write is not possible to the flash memory. So we just update this block, and then this block is returned to the new translation block. Then the physical block number for this translation block is the 23. Okay, because in place write is not possible. This updated information here is updated to the new block, and then other page translation information is just copied to the new block. Because this block location is updated, then this updated block location is also written to the physical page number of the global translation directory. Okay, so dirty. First, the dirty information table is handled. And then we know that, oh, this request is missed in cached mapping table. It's a missed. So this missed information should be found inside of the translation block in flash memory. So in order to find the appropriate translation block, then we need to access the global translation directory also. So because this logical page number is 1280, so this can be translated into 2. So this number is 2, and then we can get the physical block address for this translation table. So this translation table is accessed, and then you can get the physical page number here, and then this information is updated to the cached mapping table. Okay, so this is the missed request. Then this missed information is updated to the cached mapping table. This is the information. So 128 is mapped to the physical page address of 660. Then we access the 660 here. Oh, and then this data page is serviced to the host. Okay, so this is not a block. This is the page actually. So this is the page actually. So this is actually the page address, the physical page number for the translation. How can we say it's a page? And then this page is stored in the translation block. So because the page size is about the 4 kilobyte to the 16 kilobyte, this one page can store multiple translation information. Okay, so actually this is the page number. These pages are managed inside of the translation block. Okay, so this is the worst case of the Dftl architecture. So for this the algorithm, so you can read the paper to understand this algorithm. So what is the worst case? It's a case 3. So this worst case requires the 2 page read, then 1 page write. So the page write is required for this operation, and then page read required for this translation page read, and then data page read. So with the ideal, so very ideal page mapping mechanism, in order to read the 1 page, then we can just access the 1 page. We can just need 1 page read. But compared to this overhead, the worst case of the Dftl is the 2 page read and then 1 page write. So plus 1 data page read. Translation page read. But the ideal page level mapping just requires the 1 page read for data page. So these are the additional overhead for the worst case. So Dftl is good when accesses to storage have high locality, like cache. So this page translation information can be serviced from the CMT, like 99%. Then the performance of the Dftl may be similar to the ideal page level mapping, right? Because what if the CMT is always full and the CMT, the miss rate for the CMT is very high, then the performance of the Dftl will be very low. It may be lower than the hybrid FTL or some other FTL algorithms. Okay, so the FTL, actually the performance of the Dftl is determined by hit rate in the CMT. Okay, and then hit rate of in the CMT is determined by access patterns to the storage devices. That's very important. So that's why we need to know the characteristics of workload to develop the new architectural ideas or system ideas to the computer systems. Okay. Okay. So actually data reading is very simple for this Dftl, but data write can be a little bit complex compared to the data read. And it's also same to the other FTL mechanisms, but when the garbage collection is performed, this garbage collection may cause very high performance overhead because what is the garbage collection? With the garbage collection, then the address translation information is updated. So when the garbage collection is performed, then invalid pages inside actually there are many invalid pages in this block, and then but this block may include the valid pages. Okay. So When the garbage collection is performed, these valid pages should be moved to the other empty pages. That means that the page translation information should be updated. The ideal page level mapping, the page level mapping table exists inside of the DRAM or SRAM. Then if the location of these valid pages are changed due to the garbage collection, then we can just update the page table inside of the DRAM. But what is the problem for the Dftl? With the Dftl, this page mapping table can exist inside of the DRAM, like within the CMT, and then the page translation information is just stored in the also flash memory. So when this information is updated, then with the Dftl, then the Dftl also updates the page translation information in CMT and the page translation information in flash memory. Then if update is required, that is the that will cause high performance overhead. That is the problem of the Dftl when the garbage collection is performed. Also, the Dftl has includes the translation blocks, and then if the translation blocks are erased and then moved to the some new pages, then we need to update the GTD. Then if the victim block is a data block, then we need to update the entries inside of CMT. Also, we need to update the translation pages inside of translation blocks. So that's why the garbage collection, the overhead of the garbage collection may be high if the Dftl is applied. Okay, you can also think like this. So that's why the SSD is difficult. So that means the SSD research is not easy. So we need to consider the many aspects of the flash memory, such as write, erase, garbage collection, and rare leveling. If the new algorithm is applied to the SSD, then we need to consider these aspects of flash memory. Okay. So when the garbage collection is performed, the Dftl, the overhead by Dftl may be high. But what is the benefit? Benefit is it's good for the random write because it's basically Dftl is the page level mapping. So it's good for the random write. Okay. The problem is that random write is not good. It's still worse than the sequential write, and that's true because the random write just with the random write we need to access the CMT and the translation pages inside of a translation block frequently. Also, the garbage collection cost may be high. Okay. So also the authors of this paper compared the performance of Dftl with the other FTL algorithms like block-based FTL and then fast FTL and then ideal page level FTL. So this means that the page translation page is all translation page entries are managed inside of the DRAM. Okay. Also, the authors select some workload from the financial, cello, TPC, and the web search. And then if you see these characteristics of the workload, then you can find that the percentage of read here, and then also you can find the percentage of sequential request. Then why these metrics are shown in the paper. Because the performance of Dftl will be highly influenced by the percentage of sequential write or random write, also the percentage of read and write operations. Okay. So this this graph shows the number of merges by fast, baseline, and then Dftl. Then we can expect that the number of merges can be reduced with the baseline. The baseline means the ideal page level mapping. Well, also we can find that with the Dftl, so this number of merges can be also reduced. Also, this is important for the performance of the SSD because the avoid by partial merge or switch merge is lighter than the avoid by full merge. So if the frequent full merges are observed inside of the SSD, then the performance may be very low. So as you can see, actually the Dftl does not need to perform the full merge because it's the page level mapping mechanism. So only the partial merge or switch merges are performed inside of the Dftl. So we can find that we can expect that the performance can be improved. But as you can see, if we just see the for this workload for financial was shallow, we can find that the percentage of sequential request is extremely low. So that means that this workload includes this large fractions of random request or random write. But the TPCH, we can find that the percentage of sequential write is higher than the other workloads. You can find that number of merges by Dftl is even higher than the fast. And then, but as you can see, the number of merges by fast is also lower than the number of merges by baseline configuration. So that means for the sequential request, the hybrid Ftl can be better than baseline. But you just consider the number of merges, okay? And then block erase. But if we just see the block erase count, then we can find that with the page level mechanism, then we can reduce the number of erases. Okay, so we can compare the number of erases for the different applications like workload, the financial, shallow, and TPCH. But actually, if we just see the gap between fast and baseline, the number of erases can be dramatically reduced. Okay? It's also same to the TPCH. Because the pages are managed at a page granularity, not block granularity. So with this page level mechanism, we can reduce the number of erases. Extra read and write by address translation. So baseline is the best because it's the page level mechanism, but we can see that with the random workload, then with the Dftl, we can reduce the number of additional read and write operations dramatically, like here. But if we just see the TPCH, then the reduced number is is small compared to these workload. And then also for the authors compares the response time by fast Dftl and baseline. So page 11 here. So so I introduced the page level mapping mechanism, but this page level mapping mechanism used the caching idea, the SSD. Okay, so that means we can merge some early existing ideas to some new area like storage. Actually, this caching idea is also applied to the virtual memory. So area of the operating systems. Also, these caching ideas can be also applied to the storage, like address translation. Then Dftl used this caching ideas to the address translation. Okay, so then with these caching ideas, Dftl implements the page level translation mechanism. Then with this mechanism, Dftl can increase the performance for random request. Okay, I will stop here. So do you have any questions? Thank you for your attention, and then see you in the next class.
교수님.
네.
그냥 어드레스 트랜슬레이션 파트 2에서 마지막에 베스트 알고리즘의 프로스 앤 콘스 부분인데요.
네.
그 부분에서 이제 랜덤 라이트 로그 블럭을 룩업 한다는 게 단점이라고 되어 있는데 이거는 베스트에서도 그냥 베스트든 뭐든 로그 블럭을 사용을 하면 어차피 룩업을 해야 되니까 모든 알고리즘에 대해서 오버헤드라고
근데 많이 봐야
봐도
된다는 거죠.
네?
베스트 같은 경우에는 하나의 블락, 데이터 블락에 할당된 로그 블락만 보면 되는데
네.
이 같은 경우에는 하나의 데이터 블락에 할당된 로그 블락이 많을 수가 있잖아요.
그걸 다 봐야 되는 게
그걸 다 봐야
오버헤드다.
되니까는 그만큼 시간이 더 걸릴 수가 있죠.
네, 감사합니다.
네.
네.
네. 다 끝났나요, 질문?
네.
네.